Welcome to Lecture 4, Air Temperature. The reading for this lecture is Chapter 3 in the book. We'll be following that chapter pretty closely. And so we will start our discussion of air temperature by talking about warming and cooling of the air near the ground and how that varies over the course of a day, okay? And how therefore air temperature varies over the course of a day. Okay, we will be able to understand why temperature increases typically during the daytime after the sun comes up, and why it tends to decrease after the sun goes down. There are many applications of temperature data, such as heating and cooling degree days, that can be used to estimate energy consumption. There's also growing degree days that can be used to help determine when to plant and harvest crops. Air temperature combined with the wind speed can impact the apparent temperature one feels. Wind chill index will be discussed later in the lecture. That's a combination of cold air temperatures and wind speeds that cause heat to be lost from a human faster than it otherwise would be, and lead to a lower apparent temperature felt by the human than the thermometer indicates. And speaking of thermometers, how is air temperature measured? Okay, you probably could say yes, you probably knew it was measured by a thermometer, but what types? There's actually several types of thermometers. How do they work? Okay, we will be discussing them. So, let's start the discussion by talking about how on a sunny day with calm winds, the air near the surface can be substantially warmer than the air a meter or so up. Okay, in the United States, official weather measurements are taken at an elevation of about 5.5 feet, 1.5 meters. How tall is the average male in the U.S.? Oh, what, 5'8", 5'9"? Okay, so 5.5 feet is maybe the height of Lil Wayne, okay? And the reason that air measurements are taken not at the ground, but a few feet above it, is because at the ground, air temperature can vary much more over the course of a day. Ground heats up faster than the daytime, in the daytime than the air above it, cools down faster at nighttime than the air above it. So, in discussing each day, in a way, if the day is clear, no clouds, each day is like a tiny season as the air goes through a cycle of warming and cooling. The air warms during the morning hours as the sun rises higher and higher in the sky as the day goes on, spreading a blanket of energy over the ground. Highest point of the sun in the sky occurs at solar noon. For most of the year, that is at 12 p.m. Or near it. Actually, noon local time, local noon can be a little earlier or a little later than the actual noon time. Has to do with the fact that there's a set time for a large area, right? When we talk about time zones, right? And so if you go west or east, that's going to affect the actual time of noon. But of course, if you go west or east a certain distance, time zone's not going to necessarily change, right? So, but for a few months of the year, actually, solar noon occurs closer to 1 p.m. That's during daylight savings time. And daylight savings time takes place from spring into fall, okay? Early spring or so until mid-fall now. Actually, daylight savings time was extended by about a month 10 years ago. So, it is actually around noon when the sun's energy is most intense. Okay? We were talking about the seasons in the last lecture, and it was discussed how basically, the higher the sun angle is, the more intense the radiation is, right? We talked about the flashlight analogy for that. But the interesting point is that actually noontime is not usually the warmest part of the day, even though that's when the sunlight is most intense, greatest energy per area. The air continues to be heated, often reaching a maximum daily temperature later in the afternoon. To find out why this lag in high temperature occurs, a shallow layer of air in contact with the ground needs to be examined. As the sun rises above the horizon in the morning, the sunlight warms the ground, and the ground warms the air in contact with it by conduction. But recall from the last lecture, lecture 3, that air is a poor conductor of heat. And typically, conduction only takes place in the atmosphere for the lowest few inches of the atmosphere touching the ground. Okay, the air that's at the lowest few inches of the atmosphere is in contact with the ground, and the ground can conduct energy with it. As the sun rises higher in the sky, the air in contact with the ground becomes even warmer as it's heated from below. And there actually exists a thermal boundary, a temperature barrier or boundary separating the hot surface air, warmed from below via conduction, and the slightly cooler air above that's not warmed via conduction, but it can be warmed via convection and radiation. Given the random motion of air molecules, some can cross over this boundary. The hot molecules below bring greater kinetic energy to the cooler air. The cool molecules above bring a deficit of energy to the hotter surface air, such as through convection. But if the day is calm with light winds, this form of heat exchange is very slow, and so a substantial temperature difference can exist between the air right at the ground and the air a few feet up. This explains why joggers on a clear, windless summer afternoon may experience air temperatures of over 120 Fahrenheit at their feet and only 90 degrees Fahrenheit at their waist. So if you look at this graph, you'll see that basically at the ground the temperature is about 122, 123 degrees Fahrenheit. And only 5.5 feet up, actually, near the top of a person, it's 95 Fahrenheit. Okay. So near the surface, in calm weather, convection currents, thermals are small, and they don't efficiently mix the air near the surface, and so these large temperature gradients are able to exist. But on windier days, turbulent eddies are able to mix hot surface air with the cooler air above. This form of mechanical stirring is sometimes called forced convection, and it helps the thermals transfer heat away from the surface more efficiently. So sunny, windy days typically have less substantial temperature differences in the lowest few feet of the atmosphere near the ground than on clear, calm days. Now let's better understand the reason for the increase in air temperature during the daytime and decrease of air temperature at nighttime. Let's understand it in more detail than just, the sun comes up and warms the ground and during the daytime, okay? And then what about at nighttime, right? There's no sunlight coming in, but why does the temperature decrease? Generally, the daily variation in air temperature is controlled by incoming energy, the incoming energy is mainly from the sun, and outgoing energy emitted by Earth's surface. That's the long-wave infrared radiation that the Earth's surface emits upward that we learned about. When incoming energy exceeds outgoing energy, air temperature rises because more heat is being gained than lost. So there's a net heat gain. But when outgoing energy exceeds incoming energy, there's a net heat loss and air temperature decreases. So outgoing Earth energy is in blue, incoming solar energy in orange. Where you see the orange shade here, it's where there's more incoming solar energy than outgoing energy. And that typically starts just after sunrise, and it ends sometime in the afternoon, usually. There's a lot of factors that can affect the daily temperature variation, such as fronts, clouds, precipitation can have an impact. But this is kind of the general idea, especially on a clear day with calm winds and not much weather action, okay? We can now understand why the warmest part of the day is usually afternoon, after when the sun's energy is most intense. You see, at noon, the incoming solar energy is greatest. But even in the few hours after noontime, there's still more incoming energy than outgoing energy. And therefore, air temperature rises, as you see here, okay, reaching a maximum, in this case, at 4 p.m. And sometime in the late afternoon, there will be more outgoing energy now than incoming energy, and at that point temperature begins to decrease. That can happen, and usually does, before sunset. Okay. Here's an interesting point. The minimum daily temperature does not necessarily occur at sunrise. In fact, it's quite common for minimum daily temperature to occur about a half hour to an hour after sunrise. Okay. Wow. Mind blown, right? Why do you think that is? It's because even in the short time after the sun rises above the horizon, the radiation that is absorbed by the atmosphere is so weak because the sun is so low on the horizon that the energy is very indirect. Okay, think of the flashlight analogy. The energy is spread out over a very large area, so it's very weak per area. And it also, because of the angle, has to pass through a greater amount of atmosphere than closer to noon, so more of it gets reflected, absorbed, before it even reaches the surface. So even though there's sunlight in the morning hours for the half hour after sunrise, it's just too weak, and there's actually still more outgoing energy than what's coming in from the sun, so temperature continues to drop. Okay, very interesting. And what's also interesting about this figure here is that you can see the Stefan-Boltzmann law showing up. Remember, the Stefan-Boltzmann law says the warmer the temperature of an object, basically, the more radiation it emits. Well, notice that the outgoing energy daily curve in blue looks very similar to the daily temperature curve in red. Okay, notice as the Earth's surface becomes warmer and warmer during the later morning hours into the afternoon hours, the surface is emitting more energy. Okay, and when temperature begins decreasing in the late afternoon, early evening, the Earth emits less energy. So that's pretty interesting. How warm the surface air becomes in the afternoon depends on several factors, such as type of soil, moisture content, and vegetation cover. When the soil is a poor heat conductor, as loosely packed sand is, because the spaces between the sand help make it a poor conductor, the heat energy does not readily transfer to the ground or into the ground, which allows the surface layer to reach a higher temperature, availing more energy to warm the air above. But if the soil is moist or covered with vegetation, more energy goes into evaporating water, leaving less to increase the temperature. When the air is humid, that can lead to more haze and cloudiness, lowering the maximum temperature by preventing some of the sun's rays from reaching the ground. In humid Atlanta, Georgia, average maximum temperature in July, generally the hottest month of the year for most places in the U.S. and North America, it's 87 Fahrenheit. Okay, and that 87 Fahrenheit will often feel a lot hotter because of that humidity from the Gulf, okay? But in contrast, Phoenix, Arizona, which is in the desert southwest at the same latitude as Atlanta, experiences an average July maximum temperature of 105 Fahrenheit. Okay, it's much drier, and so there's less haze, less cloudiness to help reflect and let that sunlight in. More of the sunlight gets down to the ground and heats the surface air up. Now we can talk about how temperature varies in the lowest few feet of the atmosphere at nighttime. Okay, the previous slide we talked about how that variation is in the daytime. So at nighttime, and let's again use this example of a clear and calm night like we used for the daytime. So the winds are light and there's not really any clouds in the sky. That can lead to the air near the surface being much colder than the air above. This increase in air temperature with height is called a radiation temperature inversion. And it's called that because it develops due to radiational cooling. The Earth cools by emitting infrared radiation upward. So what you see here in this figure is that the temperature at the ground is about freezing, but the temperature at the top of your head is closer to 40 Fahrenheit. Notice that there is about an 8 Fahrenheit temperature difference between the ground and the air about 6 feet up. This is a substantial difference, although not nearly as great as the difference that can develop in the daytime when the air at the ground might be 30 Fahrenheit or more warmer than the air at the top of your head. Still, this is a noticeable difference with visible effects when we talk about crops and frost at the surface. So why does the ground and the air in contact with it become cooler than the air above it at nighttime? And the radiation temperature inversion develops best on a clear, calm night. We'll talk about why. Well, both the ground and air above cool by radiating infrared energy upward. That's radiational cooling. The ground is a much better radiator of heat than the air, so it's able to cool more quickly. Okay. Consequently, shortly after sunset, the Earth's surface is slightly cooler than the air directly above it. The surface air transfers some energy to the ground by conduction, which the ground in turn quickly radiates away. As the night progresses, the ground and the air in contact with it continue to cool more rapidly, faster than the air a few feet higher. Now the warmer upper air does transfer some heat downward, but that process is slow because of air's poor thermal conductivity. Air is a poor conductor of heat. So by late night or early morning, the coldest air is found near the ground with slightly warmer air above. Radiation temperature inversions are also known as nocturnal inversions, since they form at nighttime. And a strong radiation inversion occurs when the air near the ground is much colder than the air higher up. Sometimes the air at the ground might be 15, 20 Fahrenheit colder than the air about 6, 7 feet up. That's kind of an extreme case. What are the ideal conditions for a strong radiation temperature inversion to develop? Calm winds, a long night, and air that's dry and cloud-free. Okay, a windless night is essential for a strong radiation temperature inversion to develop because winds will help mix the air out. They'll mix the colder air at the surface with the warmer air above, and this mixing causes a vertical temperature profile that's almost isothermal or constant temperature, several feet up from the ground. And a long night is important to a stronger inversion. The longer the night, the longer the time of radiational cooling, and the more that the ground can cool faster than the air above it, right? So the longer the night, basically, the greater the difference in temperature that can develop between the ground and the air a few to several feet up. So winter nights are long nights. Okay, so winter and also later fall, especially late fall and early winter nights, provide some of the best conditions for a strong radiation inversion. The longest night of the year occurs on December 21st in the Northern Hemisphere, the December solstice, first day of winter. So some of the longest nights are in December and January. Now, radiation temperature inversions also will be stronger with clearer skies, because under these conditions, the ground is able to radiate its energy to outer space and cool rapidly. But with clouds present, much of that outgoing infrared radiation emitted upward by the surface is absorbed and then and radiation is sent back to the surface, and that slows the rate of cooling. And it's also important for the air to be dry. If it's moist with a lot of water vapor in the air, high dew point, it turns out dew point's a measure of how much water vapor in the air is in the air. Very moist air will lead to more condensation, releasing latent heat, which warms the air. In middle latitudes, the top of the inversion, the region where the air temperature stops increasing with height, is usually not more than a few hundred feet above the ground. But in dry polar regions, where winter nights are measured in months, not hours, the top of the inversion is often a few thousand feet above the surface. It may extend to 10,000 feet, a couple miles above the surface. Here's a picture of Death Valley, California, home of the hottest surface temperature ever on Earth, 134 degrees Fahrenheit, back in July of 1913. As you might expect, the highest summer temperatures tend to occur over desert regions, where clear skies coupled with low humidities and meager vegetation permit the surface and air above to warm up greatly during the daytime. During the nighttime, cold and hence denser air will slowly drain downhill and settle in low-lying basins and valleys. Valley bottoms are typically colder than the surrounding hillsides on clear and calm nights. In middle latitudes, the warmer hillsides are called thermal belts, and they are less likely to experience freezing temperatures than the valley below. So this encourages farmers to plant on the hillsides certain vegetation that are more sensitive to the cold temperatures, such as trees, certain types of trees that are unable to survive the low temperatures at the bottom of the valley. On the valley floor, this cold, dense air is unable to rise. It's colder and denser, so it's not going to rise up into warm, less dense air. And that allows smoke, dust, and other pollutants to be trapped and reduce visibility. So valley bottoms are not only colder, but often more polluted than the nearby hillsides. Even when the land is only gently sloped, the cold air settles into lower-lying areas, such as river basins and floodplains. Because the flat floodplains are agriculturally rich areas, cold air drainage often forces farmers to seek protection for their crops. Here you have temperatures of below 20 Fahrenheit at the bottom of the valley, but by the time you get to about 80 meters, 250 feet up, temperatures are now above freezing. And from about 80 meters, 250 feet, to around 280 meters, near 1,000 feet, you have a thermal belt with temperatures above freezing. But once you get above that thermal belt, you're dealing with below freezing temperatures again. Again, cold, dense air will sink to the bottom of the valley on nights, and it's essential for the nights to be calm, because if the winds are strong, that can help prevent this natural sinking of cold, dense air. Okay, can mix the air out and take away from this vertical temperature profile seen here. Now, when we talk about freezes and vegetation, we're talking about significant events. On cold nights, plants and other forms of vegetation can be damaged by low temperatures. Okay, and you might already be thinking about the Central Valley in California. You know, we live in California, the most populous state in the Union, which has one of the greatest economies in the world. Still, even after the recession, and to be fair, the state has been coming back in terms of its economy, our economy is so strong compared to many countries. And what is a major essential factor for the state's economy is our agriculture, right? We all know how so many vegetables and fruits are grown in the Central Valley, which extends for hundreds and hundreds of miles, right? From Redding through Sacramento, through Modesto, all the way south to Bakersfield. And when we get nights with strong radiational cooling, those radiation temperatures inversions can develop. We can sometimes have several hours of below freezing temperatures, which can damage crops. And so what do farmers do to help prevent vegetation from freezing and affecting our great economy? Well, on cold nights, there are a few methods of preventing vegetation from freezing. Okay, now for less large-scale vegetation, if you have a garden, you can cover your plants and shrubs with straw or cloth or plastic sheeting, which prevents ground heat from being radiated away to the cold surroundings. You could also simply wrap products with a plastic or a cover, or put cups on them. By the way, fruit trees are particularly vulnerable to cold weather in spring when they're blossoming. The protection of such trees prevents a serious problem to the farmer. The lowest temperatures on a clear, calm night occur near the surface, so the lower branches of a tree are the most susceptible to damage. Okay, the higher branches might be above freezing; they're not as likely to be as damaged. Increasing the air temperature close to the ground can prevent damage. One way this increase can be achieved is to use orchard heaters, shown here, which warm the air around them by setting up convection currents close to the ground. Moreover, heat energy radiated from these orchard heaters, which are powered by oil or natural gas, is intercepted by buds of trees, raising their temperature. By the way, early forms of these orchard heaters were called smudge pots because they produced large amounts of dense black smoke that really polluted the air, affected breathing. Okay, made the air look less pretty, right? What's prettier, a clear sky or a polluted sky? But people tolerated this pollution because they believed the smoke acted like a blanket, trapping some of the Earth's heat. Okay, the blanket analogy. Studies have shown that this concept is not as significant as previously thought. They do heat up the low air, but they don't necessarily trap the air with a blanket of pollution. Orchard heaters nowadays are designed to produce as little smoke as possible, right? To not cause health effects. Another option to help protect trees and other forms of vegetation on freezing nights is to mix the cold air at the ground with the warmer air above, raising the temperature of the air near the ground. Such mixing can be accomplished using wind machines, which are power-driven fans resembling airplane propellers. One significant benefit of wind machines is that they can be thermostatically controlled to turn off and on at the prescribed temperatures, sort of like a air conditioning unit. Or a thermostat. Farmers without their own wind machines can rent air mixers in the form of helicopters, although these are expensive to operate. So here's a wind machine. Now, if sufficient water is available, vegetation can be vegetation can be protected by irrigation. On potentially cold nights, farmers might flood the orchard. Because water has a high heat capacity, it cools more slowly than dry soil. Consequently, the surface does not become as cold if it's moist as it would be if it were dry. Also, wet soil has a higher thermal conductivity than dry soil, and so in wet soil, heat is conducted upward from the subsurface more rapidly, helping to keep the surface warmer. An orchard sprinkling system can be turned on so that it emits a fine spray of water. As you see here, you have all these sprinklers on cherry blossoms. And the reason that's done is because in cold air, the water freezes around the branches and buds, coating them with a thin veneer of ice. As long as the spraying continues, the latent heat, which is released, given off as the water changes into ice, keeps the ice temperature at 32 Fahrenheit, not less. And this ice, somewhat contradictorily, acts as protective coating against the sub-freezing air by keeping the buds or the fruit, such as cherries, at a temperature higher than their damaging point. Okay, so you might think, well, that doesn't sound safe, to flood the orchard and have the water freeze as ice on the crops. But if it's done right, where the water continues being sprayed, then that ice can protect the inner part of the crops from freezing. Okay. Care must be taken because too much ice can cause the branches to break. Here is a figure from the book showing diurnal temperature distribution above the ground. And so what you are looking at in this figure is how the temperature varies in the lowest 2 to 3 meters, about 6 to 9 to 10 feet, at different times of the day. Okay, so we've talked about how the ground warms up faster during the daytime and cools off faster at nighttime. So there's a greater variation in temperature over the course of a day at the ground compared to a few feet up, right? So these curves are basically color-coded, where the blue is the coldest time of the day, and then as you get into the red, you're looking at the warmer times of day. And you'll see here in this example at 5 a.m., the temperature at the ground is about 50 Fahrenheit, but only a few feet up, it's in the low to mid-60s. And what happens over the course of a day is the sun comes up above the horizon, heats the ground up. The ground, in turn, heats the lowest few inches of the atmosphere up via conduction, and then the lower atmosphere can transfer energy upward through convection. By 8 a.m., temperatures are now in the low 70s, both at the ground and a few feet above the ground. By 10 a.m. now, the ground is rapidly warming, and so now the temperature at the ground is 90 Fahrenheit compared to the upper 70s near your head, okay, and for much of your body. The ground and the lowest few inches of the atmosphere continue to warm up. By 3 p.m., the temperature at the ground on this day, which is probably supposed to be a clear summer day, temperature at the ground is 110 Fahrenheit. But the temperature only 3 feet up above the ground is in the 80s, okay? So just an example how the ground can really warm up a lot faster during the daytime. And typically, the difference between the temperature in the ground and a few feet up is greater during the daytime than at the nighttime, as you saw earlier. And so the diurnal or daily range in temperature continues to become smaller as one travels higher up. So here's a figure illustrating that. So the daily range of temperature, or diurnal range of temperature, it's basically the difference between the maximum and minimum temperature of the day, right? It's greatest at the ground, and it becomes progressively smaller as we move away from the surface. This is an example where you have what looks like an apartment building, but this would be a very tall apartment building. As you see, it looks like this top window is at 980 feet above the surface, and so the building is probably over 1,000 feet high. Okay, that's the height of that's probably near the height of the Transamerica Pyramid in San Francisco. In fact, I think that's higher than the Transamerica Pyramid in San Francisco. Buildings in San Jose don't get higher than 200, 250 feet because of height restrictions downtown due to the airport being so close to the city center. There are other factors that affect how large the daily diurnal variation temperature is that we'll talk about. But in this example, at the surface, daily maximum temperature is 21 Celsius, which is 70 Fahrenheit. 21 degrees Celsius, 7 degrees Fahrenheit. Daily minimum temperature is 13 degrees Celsius, or 55 degrees Fahrenheit. So that's an 8 degrees Celsius daily range, which is about 14 or 15 degrees Fahrenheit. Okay. By the time you get to 100 meters above the surface, 330 feet, the daily range is only 5.5 degrees Celsius. You see how it doesn't get as warm in the daytime, and it doesn't cool off as much at nighttime. And if you got to the top of the skyscraper, you'd have a daily range of only 4 degrees Celsius, about 7 Fahrenheit. Okay, not a whole lot of variation. So one could definitely observe a reduced heating in the daytime and reduced cooling at nighttime if they traveled from the bottom of a building to the top of a building, that building being a skyscraper. Okay, so it's very interesting. We'll also talk later about how pressure can vary greatly from the bottom of a skyscraper to its top. Now, the daily variation in temperature, or diurnal range in temperature, it's much larger on clear days than cloudy ones. The largest diurnal range of temperature tends to occur on high deserts, where the air is often cloud-free, it's dry, and there's less carbon dioxide and water vapor above the surface to radiate much infrared energy back to the surface. Okay, less of a greenhouse effect. By daytime, in the summertime, the clear skies can allow sun's energy to quickly warm the ground, which in turn warms the air above it to a very high temperature. But at nighttime for a desert, the ground will cool rapidly by radiating infrared energy to space, and for a high desert, less outgoing energy is absorbed by the atmosphere compared to near sea level. That's due to thinner air. Remember how air density decreases as one travels upward in the atmosphere? So at higher elevations, there's generally less outgoing long-wave radiation absorbed and emitted back down because the air density is less, right? There's not as much air to send the radiation back down. And that's why high elevation locations will cool off more at nighttime, right? You're familiar with that. Even in Reno, for example, which is in the high desert, daytime, it might get... Reno's about 4,400 feet above sea level, nearly a mile high in nearly a mile above sea level. In July, the maximum daily temperature is 92 Fahrenheit, right? Short sleeve weather indeed. But don't lose your shirt, or don't forget to bring an extra layer if you stay outdoors at nighttime, because at nighttime, the average daily minimum temperature in July is only 47 Fahrenheit. That's a daily or diurnal temperature variation of 45 degrees Fahrenheit. Okay. And it's not uncommon for temperatures to reach near 100 degrees Fahrenheit in Reno, and then temperatures to drop even sometimes to the low 40s, okay, at nighttime. Now, on the other hand, in humid and lower elevation regions, the diurnal temperature range is usually smaller. Haze and clouds help lower the maximum temperature by preventing some of the sun's energy from reaching the surface, okay, reflecting sunlight. And at night, that moist air keeps the minimum temperature high by absorbing the Earth's infrared radiation and radiating a portion of it to the ground. An example of a humid city with a small diurnal temperature range during summertime is Charleston, South Carolina. There, the average July maximum temperature is 90 Fahrenheit, although it feels hotter because of the humidity, and the average minimum July temperature is 72 Fahrenheit. That's only a diurnal range of only 18 degrees Fahrenheit. Okay, if you've ever been to the East Coast or the South in the summertime, you'll notice that it stays warm even during the night, right? At least in Northern California in the summertime when it gets hot, it will cool off, into generally the 60s or 50s at nighttime, whereas for much of the country, it'll stay in the 70s all night, sometimes even barely get down below 80 Fahrenheit in extreme cases, right? It makes it very hard to sleep. You really need air conditioning on the East Coast because of that. In fact, yeah, so the humidity, that moisture in the air will help enhance the greenhouse effect and prevent as much cooling at nighttime as otherwise. Okay, that's why it can stay warm overnight. In addition, if there's a lot of moisture in the air, when the temperature starts dropping, if there's a lot of moisture in the air, condensation will occur, which releases latent heat, which also keeps it warmer. So, by the way, we were talking about clouds. Clouds have the effect of reducing the daily range in temperature. So a cloudy day, on a cloudy day, all else being equal, one should expect a lower maximum temperature due to the albedo effect of clouds, and a greater minimum temperature due to the greenhouse effect of clouds. Whereas on a clear day, there's no albedo effect of the clouds, and there's no greenhouse effect of the clouds. Now, there is still the greenhouse effect from the greenhouse gases, but more on a clear day, more of that incoming solar radiation will reach the surface to be absorbed, warming it up more. And at nighttime, more of that outgoing long-wave radiation will escape to space, leading to a cooler minimum temperature than with clouds. Have a question. What are some controls on temperature? Okay, and specifically for basically average temperatures over time. Okay, so not day-to-day controls on temperature, right? The sun comes up, heats the ground up during the daytime. At nighttime, the Earth loses heat to space. But what about over as an average? Okay, over time, what are some of the controls on temperature? What can you change to adjust the temperature? There's 4 major controls on temperature. Latitude. Latitude is the angle north or south of the equator. The equator has a latitude of 0 degrees. As you travel farther north of the equator, latitude increases. Okay. San Jose's latitude is about 37 degrees north. In general, low latitudes, the equatorial regions, the tropics, are warm year-round. Okay? The reason being that the sun is always high in the sky, right? Whereas temperature tends to decrease on average as one travels to higher latitudes. That's a result of, as you go to higher latitudes, the sun angle in the summertime decreases. It's lower lower in the sky, closer to the horizon, and as you go to higher latitude in wintertime, the nights become longer. Okay, So you're all aware of this, right? You know, Alaska tends to be pretty cold much of the year, right? And North Pole is exceptionally cold much of the year, right? And then vice versa in the southern hemisphere. Okay. Another factor that controls temperature is land and water distribution. See, land heats up and cools down faster than water. Water has a higher specific heat than land, meaning it takes more energy to heat up or cool down. So water has a moderating effect on temperature. Locations closer to water generally have smaller seasonal and daily variations in temperature than those farther from water. Example, compare San Francisco and Sacramento. San Francisco is a peninsula, right, surrounded by water on three sides. To the west of San Francisco is the Pacific Ocean. To the north is the Golden Gate. And to the east is the San Francisco Bay. Sacramento is, 50 to 70 miles inland or so, or more, depending on what direction you're coming from, right? And it's another factor that determines temperature over time is ocean currents. Ocean currents can carry warm water and energy northward from the tropics into the mid-latitudes in the northern hemisphere, southward from the tropics to the mid-latitudes in the southern hemisphere. They can carry cooler water southward in the northern hemisphere, northward in the southern hemisphere. Basically, they carry warmer water equatorward from the equator poleward in each hemisphere, and they carry cooler water from the poles equatorward, and they definitely affect temperature. They can affect temperature of the ocean itself. There's a reason there are no hurricanes in California. There's a cold ocean current called the California Current off the coast. Hurricanes need warm waters for energy, and the ocean temperatures are very cold and too cold to support hurricane development off the California coast, or even not just development, but also maintaining their status. It's a different story off the East Coast. The Gulf Stream carries that warm water from the tropics off the Atlantic seaboard, and it definitely affects temperature. Okay, it's part of the reason it can be very warm, say, on the East Coast in the summertime, whereas not so warm along the West Coast in the summertime. Another factor that controls temperature is elevation. You are probably familiar with this. Generally, as one travels upward in the troposphere, air temperature decreases. This is not always true. A temperature inversion occurs when temperature actually increases with height. But in the troposphere, on average, air temperature decreases 3.6 degrees Fahrenheit for every 1,000 feet one ascends in height. Now, we can look at average air temperatures near sea level around the globe for January and July and see some of these controls showing up. Okay. First, let's look at January. These are average air temperatures near sea level in January in degrees Fahrenheit. The lines of constant temperature here are called isotherms. That's a line of constant temperature. It means equal therm, basically equal temperature. And the colors, the shading, correspond to the isotherm values. So, if I asked you, where do you find the highest average air temperatures near sea level in January, what would you say? Well, see these 80 degree Fahrenheit isotherms? Found where? In the tropics, okay? Actually, especially in the southern tropics, just south of the equator. And there's even this 90 Fahrenheit isotherm in Australia. And these are average monthly air temperatures, actually over, basically covering the days. So these aren't high or low temperatures for January. These are the average net temperatures for January over the entire month. And so if you see this 90 Fahrenheit isotherm in Western Australia, well, that means the high temperatures, the maximum temperatures, can be even higher than that, right? And this should not surprise you too much, because remember, in January, it is summer in the southern hemisphere. Now, we talked about that first control of temperature, latitude, right? Well, look what happens. As one travels to higher latitudes, what tends to happen to average air temperatures? They decrease, right? Can clearly see that. The coldest temperatures for January are found in northern Siberia, right? Soviet Russia. Here we have average air temperatures in this region of minus 50 Fahrenheit. That's just ridiculously cold, right? It's amazing how those people survive up there, where it can be too cold to even start your car, okay? And if you're out for a long period of time, you risk freezing, literally, right? Amazing. Air temperature also tends to decrease with latitude in the southern hemisphere. But notice that the gradient, the distance between the isotherms, is not as great for the southern hemisphere with respect to latitude as the northern hemisphere. In other words, temperatures don't change as fast with increasing latitude in the southern hemisphere as the northern hemisphere. Remember, it's summer in the southern hemisphere and winter in the northern hemisphere, right? Tropics are warm year-round, but it's summer in the southern hemisphere and winter in the northern hemisphere. So temperatures can decrease faster with latitude in the northern hemisphere. Land and water distribution controls temperature. Notice, if you're at a constant latitude, say you're at about 37 degrees north San Jose's latitude, so to be at a constant latitude, basically, you can't go north or south. You can only go east or west. And so if you're at 37 degrees north latitude over the Pacific Ocean and you travel east over the U.S., what happens? Temperature decreases, right? You can clearly see that as you travel further and further inland over the U.S., temperature decreases. And then when you start traveling over the Atlantic eastward, it starts increasing again, right? Everyone see that? The temperatures are colder over the interior of the North America compared to over the Pacific and Atlantic Oceans in wintertime, right? You can see the effects of ocean currents. Notice this northward tongue of temperatures and also extending northeastward into northern Europe. That's an effect of an ocean current, the North Atlantic current, helping bring warmer water to northern Europe. It's interesting because you can see that the United Kingdom here is at a high latitude. It would be basically southern to middle of Canada, and yet it's very mild for such a high latitude because of the North Atlantic current. Hey, that's good segue. That's a good transition into ocean currents, right? Our third control on the list. Elevation is another control on temperature, though that's not shown so much in this figure because the temperatures are near sea level. But if you looked at elevation, you'd see that temperatures tend to decrease with height, right? There's a reason it never snows at low elevations in Northern California, but the Sierra Nevada mountains in Northern California at the same latitudes can pick up several feet of snow each year, right? Then we can look at average air temperatures near sea level in July. And we have some changes. Now it's July, so it's winter in the southern hemisphere, summer in the northern hemisphere. Not surprisingly, the coldest temperatures are now found over Antarctica. Okay. The highest temperatures in July are found over the Sahara Desert, extending into Saudi Arabia and parts of the Middle East, as well as this area of the Sonoran and Mojave Desert in the southwestern United States. You can see ocean currents playing a role in temperatures. See this southward tongue of cooler air temperatures? That's an effect of the California current. This figure emphasizes how land and water distribution greatly impact seasonal variations in temperature. St. Louis, Missouri, and Azores over the Atlantic Ocean are both located at about the same latitude, around 40 degrees north. Yet, they have a dramatically different yearly variation in temperature. Azores' annual temperature range, and these are for average monthly temperatures, is only 14 degrees Fahrenheit, whereas for St. Louis, it's 50 degrees Fahrenheit, over 3 times as great. St. Louis has average air temperatures in the upper 20s to low 30s during winter time, whereas Azores has average winter temperatures in the upper 50s, okay, near 60 Fahrenheit. Maximum summer temperatures in St. Louis on average, and these are average, so these are in the middle, right, between low and high for each day, around 80 Fahrenheit, right, maybe lows of 70 Fahrenheit, highs of 90 Fahrenheit, but Azores temperatures do not get as high. It's also interesting that Azores' peak summertime temperatures occur maybe a month later than for St. Louis. So you see the effect of water. Because it takes more energy to heat up or cool down than land, Azores is much milder and has less variability in its annual average temperature. You can also see that for Richmond, Virginia, and San Francisco, California. Okay, not Richmond, California. I know there's a Richmond in the Bay Area, the Yay area too, right? But this is Richmond, Virginia, which is at about the same latitude as San Francisco. When two cities, such as San Francisco and Richmond, have the same average annual or mean annual temperature, 57 Fahrenheit, it might seem that their temperatures throughout the year might be similar. It might seem like they have a similar climate, right? But that's not the case. The temperature differences between the two cities are apparent to anyone who has traveled to San Francisco during the summer with a suitcase full of clothes suitable for winter weather in Richmond. Notice that the coldest month for both of these cities is January. Even though January in Richmond averages only 14 Fahrenheit, colder than January in San Francisco, shown here, people in Richmond awaken to an average January minimum temperature of 21 Fahrenheit, which is much colder than the lowest temperature ever recorded in San Francisco. Lowest temperature ever recorded in San Francisco was 27 Fahrenheit. Trees that thrive in San Francisco's weather would find it difficult surviving a winter in Richmond. Okay, so even though these two cities have the same mean annual temperature, the variation in temperature over the course of the seasons as well as over a course of a single day is quite different. Notice average summertime temperatures in Richmond are near approaching 80 Fahrenheit, whereas average summer temperatures in San Francisco barely make it into the 60s. Kind of interesting. San Francisco's warmest month tends to be September. An application of daily temperature developed by heating engineers in estimating energy needs is the heating degree day. The heating degree day is based on the assumption that people will begin to use their furnaces or heaters in their homes when the mean or average daily temperature drops below 65 degrees Fahrenheit. Therefore, heating degree days are determined by subtracting the mean or average daily temperature from 65 degrees Fahrenheit. So for example, if the mean temperature for a day was 64 Fahrenheit, there would be one heating degree day on that day. Now, on the days when the mean temperature is above 65 degrees Fahrenheit, there are no heating degree days. The lower the average daily temperature, the more heating degree days and the greater predicted consumption of fuel for heating. Now, as the mean daily temperature climbs above 65 degrees Fahrenheit, people tend to begin to cool their indoor environment using air conditioning. Consequently, an index called the cooling degree day is used during warm weather to estimate the energy needed to cool indoor air to a comfortable level. Cooling degree days are found by subtracting 65 degrees Fahrenheit from the average daily temperature. High values indicate warm weather and high power production for cooling. Now, knowledge of the number of cooling degree days in an area allows a builder to plan the size and type of equipment that should be installed to provide adequate air conditions. Also, the forecasting of cooling degree days during the summer gives power companies a way of predicting the energy demand during peak energy periods. A composite of heating and cooling degree days would give a practical indication of the energy requirements for a year. So, on Monday, just yesterday, September 19th, the average daily temperature in San Jose was 79 degrees Fahrenheit. That's for the airport. The high temperature at the airport was 94 degrees Fahrenheit. The low temperature was 63 degrees Fahrenheit, leading to an average temperature for yesterday of 79 degrees Fahrenheit. How many cooling degree days were there? How many cooling degrees days were there? The answer is 14. Yesterday was quite hot in the Bay Area, as was Sunday. There's another application of temperature data, the growing degree day. That's an index used by farmers as a guide to planting and determining the approximate dates when a crop will be ready for harvesting. There are a variety of methods for computing growing degree days, but the most common one employs the mean or average daily temperature, since air temperature is the major factor that determines the physiological development of plants. Usually, a growing degree day for a particular day is defined as a day on which the mean daily temperature is 1 degree above the base temperature. The base temperature is the minimum temperature required for growth of a particular crop. Now, on a summer day in Iowa, the mean or average temperature might be 80 Fahrenheit. On this day, sweet corn would accumulate 80 minus 50 or 30 growing degree days. Sweet corn has a base temperature of 50 degrees Fahrenheit. Theoretically, sweet corn can be harvested when it accumulates a total of 2,200, that is 2,200 growing degree days. If sweet corn is planted in early April, early springtime, and each day thereafter averages about 20 growing degree days, the corn would be ready for harvest around 110 days later, or the middle of July. So growing degree days can be used to help determine when the crop will be ready for harvest. Now, when we talk about air temperature, observed by a person, it's not always the same as the value given by a thermometer. Probably everyone realizes that the same air temperature can feel differently on different occasions. For example, a temperature of 20 degrees Celsius or 68 degrees Fahrenheit on a clear, windless March afternoon in New York City would feel almost balmy after a long, hard winter there. Yet the same temperature may feel uncomfortably cool on a summer afternoon with a stiff breeze. The human's body perception of temperature obviously changes with varying atmospheric conditions. The reasons for these changes is related to how we exchange heat energy with the environment. The body stabilizes its temperature primarily by converting food into heat, known as metabolism. To maintain a constant temperature, the heat produced and absorbed by the body must equal the heat lost by the body to its surroundings. There is a constant exchange of heat, especially at the surface of the skin, between the body and the environment. One way that the human body loses heat is by emitting infrared radiation. Humans also absorb radiation from the sun and from the air molecules. Another way the body loses and gains heat is through conduction and convection. On a cold day, a thin layer of warm air molecules forms close to the skin, which protects the body from the surrounding cooler air and from the rapid transfer of heat and loss of heat. So in cold weather, when the air is calm, there are light winds, the temperature we perceive, called the sensible temperature, is often higher than the thermometer might indicate. That warm layer of air molecules helps protect us from the cooler surrounding air. It acts as a natural insulator. But once the wind starts to blow, the insulating layer of warm air molecules is swept away, and heat is rapidly removed from the skin by the bombardment of cold air. When all other factors are the same, the faster the wind blows, the greater the heat loss, and the colder a human feels. How cold the wind makes a human feel is usually expressed as wind chill index, or WCI. The modern wind chill index was formulated in 2001 by a joint action group of the National Weather Service and other agencies. The new index takes into account the wind speed at 5 feet above the ground instead of 33 feet above the ground where the official wind measurements are usually taken. So it's more accurate in terms of being closer to where humans actually experience weather. In addition, the new wind chill index, the modern wind chill index, translates the ability of the air to take heat away from a person's face, the air's cooling power, into a wind chill equivalent temperature. So there are a couple reasons that the stronger the wind at a given temperature, the colder we would feel. One is the removal of this warm air molecule, these warm air molecules surrounding the skin. And the faster the wind, the faster those molecules are removed, and the faster the bombardment of cold molecules with the skin, the cooler we feel. But also, folks, another reason that the stronger the wind, the lower the wind chill index is due to evaporation of water. The faster the wind blows, the faster the rate of evaporation of water from the skin, and so the faster humans cool. Because remember, evaporation is a cooling process. Keep that in mind. Here is a wind chill chart showing temperature in degrees Fahrenheit on the top x-axis and wind in miles per hour on that y-axis, which goes down. And so basically, if you're given a temperature in degrees Fahrenheit, you can look at the wind speed in miles per hour to determine the wind chill index. For example, an air temperature of 20 Fahrenheit with a wind speed of 20 miles per hour would produce a wind chill index of only 4 degrees Fahrenheit. So a person in conditions with a temperature of 20 degrees Fahrenheit and a wind speed of 20 miles per hour would lose as much heat from the skin of their face as a person in calm air with a temperature of 4 degrees Fahrenheit. The coldest NFL game ever in terms of wind chill was the 1981 AFC Championship game between the Chargers and Bengals. In Cincinnati, as you might surmise, right? You're not likely to get an extremely cold wind chill in San Diego. In that game, the air temperature was -9 Fahrenheit, and there was a sustained wind speed of 27 miles per hour. So we have the temperatures in increments of 5 degrees Fahrenheit and the wind speeds in increments of 5 miles per hour, so we can't exactly figure it out, but we can get pretty close. So -9 Fahrenheit, let's say -10 Fahrenheit, wind speed of 27 miles per hour, we'll say about 25 miles per hour. And so you see the wind chill index would be about minus 37 Fahrenheit. The shading, as you can see, basically illustrates how long it would take for frostbite to occur. Where you have this light blue shading, these conditions would lead to frostbite in more than a half hour. It would take more than a half hour for exposed skin to basically suffer from frostbite. When you get to this moderate blue shading, exposed skin could have frostbite in half an hour. Exposed skin could suffer frostbite in just 10 minutes in this darker blue shading, and this purple shading, incredibly cold temperatures and low wind chill values. Those conditions would lead to frostbite in as little as 5 minutes for exposed skin. As you can see, this complicated formula here for wind chill index shows that it is a function of temperature and wind speed. Recently, in last year's NFL playoffs, the Seahawks played the Vikings in the wild card round. The game was in Minnesota. It was the last game for the foreseeable future at an outdoor stadium in Minnesota. Now the Vikings have their indoor stadium. And so this game was played with an air temperature of about minus 4 Fahrenheit and a wind speed of around 10 miles per hour. So the wind chill was around minus 20 Fahrenheit for that game. Very low scoring game. Vikings missed a field goal as time expired. I remember there was a video of Richard Sherman, the cornerback for the Seahawks, warming up running in shorts. He had on a lot of protection for his upper body, but he was wearing shorts when he was running for his lower body. Interesting what some of those football players do in cold weather, right? Some of them still won't wear sleeves even when the temperatures are down near 0 Fahrenheit. Remember, the 49ers played a cold game as well in Green Bay a few years ago in the playoffs. Right, so we were talking about frostbite. When it's cold out, exposed skin can get red or sore. This is called frost nip. And frost nip is an early indicator of frostbite. And if frost nip happens, try to get to a warm shelter quickly. Symptoms of frostbite depend on how deep it goes into the body. And there are 3 major stages of frostbite. The early frostbite just affects the top layers of the skin, whereas advanced cases can go all the way down to the muscles and bones. So the 3 stages are early, intermediate, and advanced. During an early stage, the skin will start to turn a pale yellow or white. It might itch or sting. During the intermediate stage, the skin becomes harder. It starts to look shiny or waxy. And when the skin thaws out, blisters with blood might form. If the advanced stage of frostbite is reached, the skin is very hard and cold to the touch, and it starts to darken. It may look blue and might even turn black. Some people don't know they have frostbite until it gets worse, until you can't feel the area anymore. So it's important to watch for changes in skin color. Remember, at the early stage, the skin starts to turn pale yellow or white, but it still is soft. Okay, only at the intermediate stage does it start to become harder. And we have a couple pictures of frostbite. Look at them at your own risk. But I mean, I didn't tell you that before posting the slides, so you already saw them probably. And hypothermia occurs when the body temperature drops below 95 Fahrenheit. And hypothermia is a condition when the body's temperature drops to less than that needed for normal metabolism and body functions. First symptom of hypothermia is exhaustion. Okay, someone will feel very out of breath and easily worn out. If exposure to cold continues, judgment and reasoning power can start to disappear. Prolonged exposure especially at temperatures near or below freezing, can produce stupor, collapse, and eventually, if the internal body temperature drops to 79 Fahrenheit, which is about 20 Fahrenheit below the average body temperature of 98.6 Fahrenheit, death can result. Here are the pictures of frostbite. Okay, you can see this picture, a little discoloring of the skin, and then this picture, wow, right? Not only has the skin be hardened along the fingers, the upper parts of the fingers have hardened and changed color. Okay, and frostbite tends to affect the outer extremities of the body, like fingers and toes and ears first, because they are the greatest distance from the source of body heat, which is the heart. Here is a figure showing an astronaut in space. You can see some clouds and blue sky below him. Right, he's above the Earth. And there's a capture here, 1,000 degrees and freezing to death. What does this mean? Well, in the middle and upper thermosphere, near the edges of the atmosphere and near the lower boundary of space, air temperatures can exceed 1,000 degrees Celsius, 1,800 degrees Fahrenheit. However, a thermometer shielded from direct sunlight in this region of the atmosphere would indicate an extremely low temperature. This apparent discrepancy lies in the meaning of air temperature and how it is measured. Recall from Chapter 2 that air temperature is directly related to the average speed of air molecules. The faster they move on average, the higher the temperature. In the middle and upper thermosphere, at altitudes approaching a few hundred kilometers above the ground, air molecules are zipping about at speeds corresponding to very high temperatures, right? In the upper thermosphere, the air density is so low that the molecules have such great spacing that they move very fast. However, in order to transfer enough energy to heat something up by conduction, like exposed skin or a thermometer bulb, an extremely large number of molecules must collide with the object. In the thin air of the upper atmosphere, air molecules are moving extraordinarily fast, but there are simply not enough of them. Density is too low to bounce against the thermometer bulb to have it register a high temperature. When properly shielded from the sun, the thermometer bulb would lose far more energy than it receives and indicate a temperature near absolute zero. This explains why an astronaut, when spacewalking, will not only survive apparent temperatures exceeding 1,000 degrees Celsius, but will feel a profound coldness when shielded from the sun's energy. At these high altitudes, the traditional meaning of air temperature, regarding how hot or cold something feels, is no longer applicable. How is temperature measured? With a thermometer, as you know, but there's a few different types of thermometers, okay? Typically, daily temperatures are measured at automated weather stations. Automated weather stations are usually found at airports. And there's a few types of thermometers that can be used to measure temperature. Highly accurate temperature measurements may be made with electrical thermometers or electrical resistance thermometers. That's one type of electrical thermometer. An electrical resistance thermometer does not actually measure air temperature, but rather the resistance of a wire, usually platinum or nickel, whose resistance increases as temperature increases. An electrical meter measures the resistance and converts it to air temperature. And these electrical resistance thermometers are what are often found at the automated weather stations. Your car thermometer may use an electrical resistance thermometer, as may a digital thermometer at home. Thermistors are another type of electrical thermometer. They're made of a ceramic, which means it forms clay when it becomes harder, and it's a clay-like material that hardens over time. They're made of a ceramic material whose resistance increases as the temperature decreases. Okay. A thermistor is the temperature measuring device of the radiosonde. That's the instrument that is attached to a weather balloon and measures air temperature at altitudes of up to several to tens of kilometers above the ground. Another electrical thermometer is the thermocouple. This device operates on the principle that the temperature difference between the junction of two different types of metals sets up a weak electric current. When one end of the junction is maintained at a temperature different from that of the other end, an electric current flows. The current speed is proportional to the temperature difference between the junctions. Now, these three sensors are all electric or electrical thermometers. There are others, such as the liquid in-glass thermometer, shown here. This is an Accurite liquid in-glass thermometer. Most of these liquid thermometers use alcohol, maybe mercury. Here you see what would the temperature be, right? About 70 Fahrenheit or 21 degrees Celsius. Basically, these work like so. As air temperature increases, the molecules in the liquid, alcohol or mercury, move faster, acquire greater speed, so the distance between the molecules increases and the liquid expands. Okay, liquid expands, and so you read a higher temperature. Conversely, if temperature cools, molecules move slower, crowd closer together, so the volume of the liquid decreases. Okay, and so the temperature appears lower. You can buy one of these liquid in-glass thermometers for, what, a few dollars at Walmart or on Amazon. There's also an aneroid thermometer. That's a thermometer that kind of looks like a clock. It has, but instead of, so it has a dial that points to a number, but instead of having time numbers, right, like 12, 1, and 2, it has temperatures. Basically, on the other side of that aneroid thermometer, there's some sort of metal, usually, or typically a metal that expands in the heat, contracts as temperatures cool, and that expansion or contraction, folks, changes the direction the needle points, or the hand points. Here's a picture, beautiful picture of a portable remote weather station. We'll learn more about more instruments as we go along. But this here, see this, it looks like 3 bulbs here. This device, this is an anemometer that measures wind speed. And this device is a wind vane, it measures wind direction. But the thermometer, and as well as the hygrometer, which measures humidity, would be inside of this shelter. That brings up a good question. Why is a thermometer shelter needed? Well, it's impossible to measure air temperature accurately in direct sunlight. In direct sunlight, the thermometer will absorb energy from the sun in addition to energy from the air molecules. The thermometer will gain energy at a much faster rate than it can radiate away, and so the liquid will keep expanding and rising until there is an equilibrium between incoming and outgoing energy. Because of the direct absorption of sunlight, the level of the liquid for a liquid thermometer would indicate a temperature much higher than the actual air temperature, right? So a statement saying today's high temperature in the sun will be 100 degrees has very little meaning. It is important to keep thermometer in a shady place to measure the temperature of the air accurately, right? You don't want to measure the temperature in the sunlight. You want to gain an appreciation for air temperature. And if you have your thermometer exposed to sunlight, it's not only going to be heating up, it's not only going to be gaining energy from the air molecules, but from the sun as well. Okay? So the shelter is needed for shading. Why are vents needed? Because one wants to determine ambient air temperature. If there are no vents, it will get too hot inside, and the temperature, the thermometer will be inaccurately high. Okay, we need vents to get that ambient air inside. Finally, notice that the shelter is colored white, and that is to prevent, again, absorption of sunlight. If the shelter was black, then the thermometer would heat up too much because the shelter would be absorbing sunlight, right? So the shelter is painted white in order to avoid absorbing sunlight and leading to an inaccurately high temperature. So don't trust every thermometer reading you see. Bank thermometers are notoriously inaccurate because often the thermometer is placed on the roof of a bank in direct sunlight. Okay. All right, that's it for lecture 4 on air temperature.